Hi guys. Hopefully you had as much fun watching that demo video as I had making it. I promise no children were harmed in the making of that video. At least that's what I'll stick with. Um, all right, back to our regularly scheduled program. Something, something, something. Um, did you all see the answer on the multiple choice? Hopefully you didn't. All right, I had this contraption that I did the demo on, which was basically a solenoid, and we had a bunch of currents running through that solenoid. Um, and we'll pretend that at the moment I turned it on, that the current was running around just like I talked about in the video, and that the magnetic field due to the solenoid was directed upwards. Um, Now, in fact, maybe it was directed upwards, but I also had it plugged into the wall, right? And we know that the direction of the current cycles 60 times per second when we're talking about AC power out of the wall. So initially, in the first 60th of a second, it might have been upwards and then downwards and then upwards and downwards and upwards and downwards and so on and so forth, as that direction of the current and that solenoid constantly changed back and forth. That's part of the reason why we saw such a big reaction, just a big jump, especially on that one ring that I used, is because of the fact that the solenoid constantly had a changing magnetic field. Now, that's actually what's going on, but what I'm going to do is I'm going to just focus in on that first instant in time because honestly, conceptually, the physics that I want to talk about doesn't change much for DC rather than AC. For AC, we see basically a bigger result, but we would see the same type of behavior for DC. All right, so we're going to pretend that our initial magnetic field was zero. Well, when I've got the current off, it's definitely zero. And then when I activate the current, we're going to pretend that the magnetic field due to the solenoid is upwards. So I'm going to use that information, that framing, to ask the following question. So if I've got my magnetic field due to my electromagnet, when I say electromagnet, that's just solenoid, is what I mean there, solenoid. It's a magnetic field that's caused by electricity. If the magnetic field due to my electromagnet goes from zero to upwards when I depress a switch, then what's the direction of the induced magnetic field from the jumping ring of wire at that moment, right? So my solenoid magnetic field goes from zero to upwards. What's the direction of the induced magnetic field due to the jumping ring at that moment? Also, with that information, what's the direction of the current in the ring of wire if we're viewing that ring of wire from above? Okay. So props help on this. There's my ring of wire. You can use your left hand as your ring so that you can use your right hand for right hand rule number 2, or whatever you need to do. And you need to try to use Lenz's law to answer this question. And I really do want you guys to think about this actively and see if we can come up with the right response. So at this moment, please pause the video. So pause. It's me twiddling my thumbs. I'm wasting both my time and your time. What's the answer? B. The answer is B. All right. Why is the answer B? Well, we go from no magnetic field to having all kinds of magnetic field upwards. So no magnetic field to having all kinds of magnetic field upwards. We got all kinds of magnetic field, all kinds of flux going upwards through this ring. Well, the ring doesn't like that, so it tries to maintain the status quo. It tries to cancel out that change. So in order to cancel out that change, what does it have to do? Well, it has to set up its own magnetic field that is downwards, which is easier for me to say than do. So it goes from zero to having all kinds of field upwards. It sets up its own magnetic field that's downwards to try to compensate for that change. So the correct choice here has to be either choice B or choice D? Now, the magnetic field, we figured out is downwards. And now we have to view this from above. So our fingers go downwards. Our thumb is going to tell us the direction of the magnetic field. And I can tell you that by looking down at this ring right now, that the direction of, I think I stumbled over my words. The induced field is downwards. Our thumb is going to tell us the direction of the current. Excuse me, I think I said magnetic field. I meant current. Fingers are magnetic field, thumb is current. And now I can tell you that as I look down at this ring, it's very clear to me that my thumb is pointing in the clockwise direction. Let me change the perspective so that you guys can see it. There we go. If I do that, you guys can see that my thumb is pointed in the clockwise direction. Okay, and the perspective I'm showing you right now is a perspective that has basically the camera above the ring. And now my thumb is tracing around and going in the clockwise direction, which I have to tell you, the camera is on one side of this and I'm on the other side, and it's weird for me to say that. But yes, from above, which is what you're staring at, the thumb just definitely points in the clockwise direction. So choice B is the right choice. And that's how we figure out this problem with Lenz's law. Now, I said in the demo slide 2 slides ago that we're actually working with AC current rather than DC current. So when I depress the switch, I go from having no magnetic field to, I don't know, maybe initially the magnetic field is upwards, but at the next moment it's going to be downwards and then upwards and downwards and upwards and so on and so forth. Well, I've got a constantly changing magnetic field. And as a result, this thing really hates that, because what's going to happen is if I've got all kinds of flux upwards, coming from 0 to all kinds of flux upwards, it sets up its own field downwards. But then at the very next moment, my permanent field, my AC field goes downwards, and then it sets up its own field upwards. And so these two magnetic fields are constantly repelling each other. The induced field in the wire, or in the ring, and the permanent field, the field from the solenoid, are constantly basically squared off against each other, repelling one another, pointing in different directions. And that's why we see such a big jump in that ring. All right, I think that nails that. We'll have some more examples of Lenz's law coming up.